Electromotive force and the internal resistance. When we have a supply which convert the chemical energy to electrical energy, say you're buying a cell, you're buying an unused cell, and on the cell it is labeled 1.5 V. So you buy a cell and on the cell it is labeled 1.5 V. If I connect a voltmeter across this cell, how much reading the voltmeter should give? The cell is unused and it is labeled 1.5. So what should be the reading on the voltmeter? So it should be 1.5. But practically what happened? Yeah, it should be 1.5 because it is an unused cell. But what happened when we buy even an unused cell? What we found that what is labeled on the cell, it does not give the same voltage. It won't be 1.5. It may be less than 1.5, maybe 1.45, maybe 1.4, but not 1.5. So what is the reason why we don't get the same voltage what is labeled on the cell? Because inside the cell, it is having its own resistance, and what we call that as an internal resistance. So because of the internal resistance, some of the voltage lost inside. When the charges are moving, the charges are flowing because the cell is having its own resistance. So we don't, the sum of the energy or the sum of the voltage is dropped internally. As a result, we don't get the same value what is labeled. We always get a smaller value what is labeled on the cell. So the internal resistance, the term internal resistance refers to resistance of the cell or a battery. And what is the evidence of the internal resistance? The evidence of the internal resistance. So when you allow the current to flow through a cell or a battery, you never get the same voltage what is labeled on the cell. You always get a smaller value what is labeled on the cell. So if on the cell, so most of the question in electrical circuits, we assume that the cell is having no internal resistance. Like for example, if I say 3 volt supply is there and you connect a resistor, so how much voltage will be there? 3 volts. But what is there is based on the assumption that the cell is having no internal resistance. But practically, when you connect a cell and a resistor in the circuit, this will never be 3. It will be less than 3, any number, but it will always be less than 3. Because when the charges are coming out from the cell, they have lost some of their energy because of the resistance of the cell. So they will not have 3, they will have less than 3, any number like 2.9, 2.95, 2.8, any number, but it will be less than 3. So when the charges lose their energy because of the resistance of the cell, we call that as internal resistance. So if we draw a cell with an internal resistance, if we connect a cell and on the cell it is labeled 5 volts. So what should be the voltage across the resistor? Theoretically, it should be 5. Why? Because the voltage of the battery should be same as the voltage across the component. And according to the Kirchhoff's second law, the total EMF must be equal to total potential difference. But when you measure this, you connect a voltmeter, you never find that the voltmeter reading is 5. It is less than 5, maybe 5.9. So what happened to 0.1 volt? That 0.1 volt is lost because of the internal resistance of the supply. So how we draw a battery with internal resistance? So most of the question in electricity are assume that there is no internal resistance. Assumption is there. So how we draw a cell with internal resistance? So we draw a cell, then we draw a symbol for the resistor. Then in a box, the dotted lines. So this is a cell with the internal resistance. And then we connect this resistor. So what actually happened? So this is a 5 volt supply. So out of 5, maybe 4.9 volts here and remaining 0.1 volts will be across the internal resistor. That's why when you connect a voltmeter, your voltmeter will never record 5, it will record less than 5 because some of the energy is lost because of the internal resistance of the supply. Is it clear, the concept of internal resistance? So how we derive a formula for the internal resistance and compare with a how we derive a formula for internal resistance and compare with the voltage of a cell. So let's say this is a cell with internal resistance. And it is connected to external resistance. External resistance is R, internal resistance is small r, and the EMF is E here. The current which will flow, that will be I through the external resistance, and I will be the through the internal resistance. If we apply the Kirchhoff's second law, according to Kirchhoff's second law, in a loop, in a closed loop, the total EMF must be equal to total potential difference, or the sum of EMF, electromotive force, must be equal to sum of potential difference, or PD. So EMF of the supply, that is E here. What is the voltage across external? V is equals to IR. So voltage across external will be IR. So the potential here will be IR, which we can also say V, plus what is the potential here across internal? That is also I, but small r. So this will be equals to I small r. Because V is equals to IR, so voltage here is current into external resistance, and voltage here is current into external resistance, internal resistance. So if this was like a 10-volt supply is there, so maybe 7 volts is across external. So how much voltage will be across internal? 3. If it is a 10-volt supply, if 5 volts is across external, how much voltage will be there across internal? 5. If this is a 10-volt supply, if the 2 volts is external, how much voltage will be there? Internal? 8. The total sum should be same. So the total EMF must be equal to total potential difference. So we can say EMF is equals to the current in the circuit into external resistance plus the current in the circuit into internal resistance. This is one formula. Or we can also say that V is equals to IR. So we can substitute that EMF is equals to external voltage plus internal voltage. So we can also say that EMF is equals to V plus IR. Is it clear, this formula? So this is a formula which is used to solve the question when a battery is there with a internal resistance. So this is a voltage drop external, and this is a voltage drop internal. Where small r is a internal resistance, capital R is external resistance, and E is the EMF of the cell, the maximum voltage of the cell. So whenever you see a question, a battery with internal resistance, then this will be your formula. EMF is equals to V plus IR. Now we can also, they asked to sketch a graph also. So I'll explain the graph for the voltage and the current. If we have voltage on y-axis and we have a current on x-axis, and we want to explain the graph for the battery with internal resistance, what will be the shape of the graph? So let's say we want to sketch a graph for the battery with internal resistance, the voltage and current. Voltage on y-axis and the current is on x-axis. The circuit which we are using here, this is a battery with the internal resistance small r, and the EMF of the battery is E. External resistance is capital R. And the external resistor which we connect here is a variable resistor, okay? And we connect a voltmeter. We connect a voltmeter across the, it can be connected here as well, like it will not make difference. I can connect a voltmeter here, or I can also connect across the fixed variable resistor as well. It's the same thing, no difference. And we connect an ammeter at this point. We have the formula that according to this formula, the example that if the current I is there in the circuit, that the EMF is equals to V plus IR. Now, in the beginning, we start with a very high resistance of R. R is very high. If the R is very high, it does not allow the charges to flow. Like it's so high that it is not allowing the charges to flow. Because, for example, if you are holding a cell in your hand, do you feel any electric shock? You're holding a normal dry cell in your hand. Do you feel a shock? No. Why you don't feel any shock or like no current passes through? Because your body is having a very high resistance compared to the cell. So same idea that this cell is having a very low voltage and this is having a very high resistance. So as a result, there is no current in the circuit because of very high resistance. So same, it's the same concept. Like if I'm holding a cell in my hand, that there will be no current in the passing through the from the cell or passing through my body and into the opposite terminal because my body resistance is very high compared to the cell power to derive the charges. So this in variable resistor is having a very high resistance in the beginning. When it is having a very high resistance, the current initially is zero. So if the current is zero, so this factor will be zero because there is no current in the circuit. So 0 multiplied by anything is 0. In that case, what will happen? The EMF will be equals to V. Means when the current is 0, we'll have a maximum voltage and that maximum voltage will be equals to EMF. Is it clear this point, the first point? So voltmeter will record the same value as the EMF. Like on the cell, if it is labeled 9 volts, the voltmeter will record 9 volts. Why volt? Because there will be a loss voltage internally if there is a current from the battery. If there is no current from the battery, there is no current. In that case, the EMF will always be equals to voltage reading on the voltmeter. Then what happened? We gradually start to reduce the resistance. As we start to reduce the resistance, so we have the formula EMF is equals to V plus IR. Voltmeter record the potential. It's not like even the charges flow or does not flow. Even a charges flow or does not flow, the voltmeter record the potential difference in the cell. Like one end of a cell is having 9 volts, another end is 0 volts. And when we connect a voltmeter, so voltmeter record the potential difference in the voltage. So that's why it recorded 9 volts here. Irrespective that there is no current in the circuit. Voltmeter record the potential difference. So when the current is 0, the EMF will be equals to the external voltage. Now what happened as we gradually reduce the resistance, so the current start to flow. As the current start to flow, so there will be current will increase. So if the current will increase, this factor will increase. If this factor will increase, like IR will increase. So what will happen to the voltage across the battery or a supply? The voltage across the battery or a supply will decrease because EMF is constant. So the sum should remain same. If the internal voltage is increasing, like more voltage is drop internally, so less voltage will drop externally. Like when we allow the current to pass, so maybe 2 volts is here. If 2 volts is here, how much voltage across the voltmeter? 7. If the voltage here is, let's say, 3 volts, so how much voltage will be there across the voltmeter? 6. Because the total should be 9. If the voltage here is 4 volts, how much voltage will be here? 5. If the voltage here is 5 volts internally, how much voltage will be external? 4. Because the total sum is 9 here. If the voltage internally is like, let's say 6, how much voltage will be here? 3. If the voltage here is, let's say 7, how much voltage will be here? 2. So as you can see, if the voltage internally increases, the voltage external will decrease. And voltage internal depends on how much current is passing. So as a result, what will happen? When the current is increasing, the voltage reading is decreasing, the voltmeter reading. So eventually what will happen? We'll have a graph like this. So when we join the points, it will be a straight line. And the slope of this graph, the slope represent the negative of the internal resistance. So using the slope or the gradient, we can find the internal resistance of this supply. And the y-intercept, when it intersect the y-intercept, what y-intercept represent? The y-intercept represent the EMF or the maximum voltage of the supply. So whenever we have a graph for a voltage and current for a battery with internal resistance, it will always be like this, in which the y-intercept represent the maximum voltage and the slope of this graph represent the negative of internal resistance. Or you can use it to find the internal resistance. Is it clear, this concept of internal resistance and the graph? Anyone having a doubt or a question in this? So how the EMF is equals to negative of internal resistance? So you can use a mathematical equation like, see, we can derive we can compare this. So we have the formula that EMF is equals to V plus IR. If I rearrange the equation, I can say EMF minus IR is equals to V. Or I can also say V is equals to minus IR. Like I just rearrange the equation plus E. Or I can also say EMF V is equals to minus RI plus E. So when I compare this with the equation of a straight line, which is y equal mx plus c. So on y-axis, if we have a voltage, on y-axis we have a voltage. On x-axis we have a current. So on x-axis we have a current. So what will be the gradient of this graph? The gradient of this graph will be equals to minus r. So when you take a gradient or a slope, you will get the negative value, like you will get a negative gradient. So negative value, like say when you work out a gradient, your gradient is say minus 3. So minus 3 is minus r. So r is equals to 3. So when you work out the gradient of this graph, you will always get a negative value. As you can clearly see that the x1, y1 is greater than y2. So definitely the gradient will be negative. And the y-intercept, when it intersect the y-intercept represent the EMF of this internal, EMF of this cell with an internal resistance. So example, an alkali cell with an EMF of 1.5. So there is a cell with the EMF means maximum which get provide. So that is 1.5 volts. Internal resistance of 0.1. So 0.1 ohm is the internal resistance. Is used to supply power to a toy electric motor car. The resistance of a motor is 1.4. So there's a resistance of a motor is 1.4 ohm. That is external. Find the current and the potential across the motor, like how much voltage is there and how much current is flowing through this. So how we can work out, we have the formula, the EMF is equals to the voltage external plus voltage internal. The current here is I and the voltage external is V. This is one formula. But the problem, we cannot use this formula right now. Why we cannot use this formula? Because we don't know what is the potential here, that is unknown, and we don't know what is the current here. So two unknowns are there. That's why this equation cannot be used. Then what else we can use? We'll use the concept, the Ohm's law, that the resistance is a ratio between voltage and current. So if we know the total resistance of the circuit, we know the total voltage, then we can find the total current in the circuit. So what is the total resistance of the circuit? You can see how these two resistors are connected. How the two resistors, the motor and the internal resistors are connected. They are connected in series. One way for the charges to move. So what will the total resistance of the circuit? The total resistance of the circuit will be, as they are in series, 1.4 plus 0.1. That's a total resistance. So which is 1.5. The total voltage, what is the total voltage? The maximum voltage, that is 1.5 as well. And we need the current. So when we simplify, this is 1.5 is equals to 1.5 over I. So I is equals to 1.5 divided by 1.5. So I is equals to 1 ampere. So the current which will flow, that is 1 ampere, will flow through each of them as they are connected in series. Now, if we want the potential now, like how much voltage is here, we know the current and we know the resistance. So we can use a formula like this value, or we can also substitute in this one. We'll get the same answer. So V is equals to IR, where I is the current, which is 1, and R is the resistance, 1.4. So 1 into 1.4, so we got 1.4 volts. So 1.4 volts will be their external voltage. If external voltage is 1.4, how much voltage will be internal? The internal voltage will be 0.1. Because the sum of the internal and the external voltage should be equals to EMF, or the electromotive force. Then we have different types of circuits. Like example, normal circuits are there, or a closed circuit. So if this is written 3, how much voltage will be here? It will also record 3. This is an open circuit. The circuit which is having like no complete components are like loop is open. No, it's not closed. So this is the open circuit. And this is a short circuit. What is the meaning of a term short circuit? The term short circuit means a circuit with no resistance. That is we call as short circuit. So for this case, like if the resistance of a lamp is R, if a resistance of the lamp is R and EMF is E, the current I is there and internal resistance small r. So when there's a current, we can use a formula that EMF is equals to V plus IR. V is the voltage across it, I is the current passing. So we can use this formula. When there's an open circuit means like a circuit with no current in it. That's the open circuit. So when I is 0, we can say EMF is equals to V. Like if we connect a voltmeter here, the reading on the voltmeter will be same as the reading of the supply. Why? Because there is no current in the circuit, or the value of, if there is no current in the circuit, means the value of, there will be current in the voltmeter, but that is negligible. You can neglect that current. Practically, yes, there will be a current in the voltmeter, but we are neglecting that. So if we have an open circuit, in that case, the EMF will be equals to voltage. And if we have a short circuit means there is no external resistance. So in that case, EMF is equals to IR, because we have the formula that the EMF is equals to V plus IR, or we can also say EMF is equals to I capital R plus I small r. So in this circuit, R is 0, external resistance is 0. So in that case, the EMF is equals to IR. If we have no current, then EMF is equals to V. And if there's a current, then EMF is V plus IR. So three different scenarios are there depending on the circuit. This is the same graph as I just explained about a variable resistor connected, a voltmeter and ammeter is there. Power and load resistance graph. Like, say we have a battery with an EMF of 10 with internal resistance of say 5 and external resistance is there, and we are changing the external resistance, and we want to plot a graph. We want to plot a graph between the load resistance, this is a load resistance or external resistance, and the power. And what is the formula for power? You can use a formula P is equals to IR, or P is equals to VI, or you can also use P is equals to I square R or V square over R, any formula. We'll take different examples. Let's say the value of R is 2 in the first example. So if the value of the R is 2, what will be the current here? So EMF is equals to I capital R plus I small r. So I can take I common. The EMF is 10. The current we don't know. The external resistance is 2 and the internal resistance is 3. So 10 is equals to, so this will be 10 divided by 7. 10 divided by 7 is what? So it will be 1.8, 1 point, 1.4, sorry, I mean, 1.43. So 1.43 ampere. So we have 1.43 ampere, and what about the power? P is equals to I square R. Because we know the current and we know the resistance, so we can find the power. So it will be 1.43 square times the resistance is 2. 1.43 multiplied by 1.343 square multiplied by 2. What's the power? What is the power here? 1.43 square into 2. So we got 4.1 watts. Okay. So the power here is 4.08, which is 4.1 watts. So when the resistance, and now we are comparing because we want to sketch a graph. So when the resistance was 2, the load resistance was 2, the power was 4.1. Now we change the load resistance to a new value. Let's say the load resistance is now 5. So if the load resistance is 5, now we'll solve for the first the current. What is the current? So this is 10. I is unknown. The load resistance is 5 and the internal is also 5. So 10 divided by 10, which is 1. So current is 1 ampere. What about power? So it will be 1 square multiplied by resistance, which is 5. So 1 square multiplied by 5. So we got 5 watts. So when the resistance is 5, the power is also 5. Okay. Now we are increasing a resistance to a new value. Let's say we make it 8. Now we are taking the EMF, which is again 10. The current we are finding, what is the external resistance? Now the external resistance we are taking as 8. So this will be 8 plus 5, which is 13. So what is the current here? It will be 10 divided by 13. What is 10 divided by 13? So 0.77, we'll get the current as 0.77 ampere. And now we're finding a power. So this power is external power. So that's why we are not taking the total resistance. We are only taking external resistance. So 0.77 square multiplied by 8. What's the answer? 0.77 square multiplied by 8. So we got 4.7. 4.74 or 4.74? 4 or 4 or 4.7. Okay. So as you can see, when we are increasing a resistance, the power was increasing. It was having a maximum value and then it decreases. So what it give an idea that when for external power and the load resistance, what is the relation between them? If we have a power on the y-axis and we have a load resistance or external resistance on x-axis, so when we are increasing the resistance, the power is increasing. And then when we further increase the resistance, the power is decreasing. What is this value of a resistance when we have a maximum power? So when we have a maximum power, like the power is maximum, what it give an idea at this point, the resistance which is out is same as resistance which is in. When internal resistance, like internal resistance was 5 and external resistance is also 5, when two resistors are same, in that time we'll have the maximum power output. So if we want the maximum power output from the cell, we should make the internal and external resistance same. If the external resistance is higher than internal resistance, we'll get a lower power than maximum. If external resistance is lower than the internal resistance, we'll also get a lower power. But it is maximum when the internal and external have the same resistance, the power output. So that is why the shape of the graph between it will be zero, but it will take much longer time. That's why we just sketch for a region. That's why we did not make it completely zero. It will be, but it will take the increase is much greater as compared to decrease. So gradually it will decrease and eventually it will reach zero. So the relation between the power and the load resistance, that if you increase the resistance, the power will also increase. It reaches a maximum value. When it reaches a maximum value, when the internal and the external have the same resistance. Is it clear, this concept? Any doubt in this?